the agenda for today is, well, for yourself, it's going to be a lot of revision on derivative stuff. So I guess when we hit the breakout rooms, it can be more targeted to where you're currently at. Just for the sake of the recording, and anyone else who's doing this for the first time, I'll go through the content. But if no one comes in who is doing this for the first time, I'll just kind of speed things up a little, and then they can just sort of use the pre-recorded stuff to help out there. But okay, so some fundamentals of the derivative. So the gist of what we're doing here is we have some function and we want to know the gradient of that function for particular values of x. That's what derivative is all about. So when you find this function called the derivative, what you're doing is you're creating a function that has that tells you the gradient of the original function for any possible value of x. So before we get into the nuances of how that works, let's say this is our original function, x squared, and then the derivative of that function is 2x. What that means is, if I sub in a specific value of x into f dash, so into the derivative, whatever comes out of this is the gradient of the original function for that particular value of x. So if we just sort of draw, if we draw an example of what that would look like, got our axis, we got our quadratic x squared. At x equals 2, for instance, if I were to sub in x equals 2, I would be looking at this particular spot on the graph, on the handwritten section. So for x equals 2, the y value of that's going to be 4, obviously. You've got y equals x squared as the graph. 2 squared gets you to 4. But we have our function f dash of x, which also tells us the gradient at x equals 2. So if we sub in 2 into f dash of x, which by the way was 2x, you have 2 times 2, which is 4. And so basically what we've just achieved is the slope of this curve at that spot is 4. 2 times 2 gets you 4. So the slope at that spot is 4. That's what we're doing with derivative. When you have your function that is a derivative, you sub in particular x values that tell you the gradient of the original function at that spot. As for how you do derivative, you look up a table of values. So if we go back to the screen share, you'll notice that you have different kinds of functions. And then on the right-hand side of those are the derivatives of those functions. So for instance, if you have any power function, x to the power of n, finding the derivative of that, that's what that notation is all about, is just a matter of bringing the power down the front. So n comes from being the top down to right beside the x, and then that power of n gets reduced by 1. We see an example of this here. Right, this is x to the power of 2. So n is going to be 2. So the 2 drops down to the front, and then you subtract 1 from the 2 on top. That's how we got to 2x in the first case. That's how it works for power functions. For all sorts of other functions, derivative of e of x is just itself. Derivative of the natural log is 1 over x. Derivative of sine is cos. So on and so forth. We use a table of values or a table of derivatives rather, to figure out what the derivative of a function is. How to do more complicated ones, you essentially do them separately. So we have this big function that has both a sine and a natural log in it. You're essentially using these properties to split things up. Now, as you get more and more familiar with what's going on, you don't go into this much detail to try and do the derivative. You would just go straight into it and do it off the bat. However, what's happening under the hood is essentially you're seeing that you have two separate functions separated by either a subtraction or a plus sign, right? Plus or minus. And so what that means is when you have that scenario, instead of doing the derivative of the entire thing, which technically doesn't exist on the table, you split it across two separate derivatives. So instead of doing this whole thing, we now split it between derivative of 4 sine x minus derivative of 2 natural log x. We're splitting those up. Then from there, technically speaking, we haven't seen what happens when there's a coefficient at the front. Right, this is 2 natural log x. This is 4 sine x. we haven't seen any of those numbers at the front of these things. So technically, we should know how to handle that. Obviously, we do as we get better of doing things. We're implicitly doing this, which means anytime you have a constant coefficient at the front of your function, you can take that out the front, do the derivative of the function, and then bring it back in as a multiplication. So for instance, instead of doing derivative of 4 sine x, you take the 4 out the front, do the derivative of sine, and then put that back in. Because when you get to this stage, you can look at it on the table of derivatives. You can see that the derivative of sine is cos. So you have this term that says derivative of sine, you replace it with cos. And the 4, well, that's obviously just going to drop back down. This is in a lot of detail, mainly for anyone who hasn't done it before. Is there any questions as to at least how we find derivative? I'm happy to go into or cover anything that was a bit weird about that. And if I go too fast, just like raise a hand or hop off mute. That's totally fine. Yeah, this stuff is in there. Why not? There's no real questions around this. This kind of question can show up pretty much anywhere, even in functions and relations, like pre-calculus. For increasing and decreasing functions, the reason why it's in here is because you can also talk about things in terms of gradients. Like for instance, an increasing function just means that from left to right, the y values are always getting either bigger or plateauing. That's for regular increasing. For decreasing, it means the y values could be getting smaller or plateauing. So to draw a few examples of that, here's an example of an increasing function. Increasing, 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 increasing. Now pretend that's perfectly flat. I know there's technically a dip in there. Pretend I have a steady hand. That would be considered an increasing function. So this increasing. For decreasing, should be fairly obvious. It'll be basically the opposite. All right. You have a function that's going down, 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 maybe plateaus, down, maybe plateaus. The reason why I'm highlighting this is because there is an adjacent term, which is strictly increasing or strictly decreasing, which basically means you can't have these plateaus. Not allowed to have them. So when you have strictly increasing, it'll usually look like a curve that's always pointing up, either in a linear way or in a up and like concave up sort of way. Or I guess even concave down technically works as well, because it's still increasing, as long as it's always going up, left to right. Same thing for strictly decreasing. That's the differences between those. Now, one thing worth highlighting, which is the questions that typically get asked around this is, over what interval is a thing strictly increasing or decreasing? That's where it gets trickier. Because when you have a graph like, how to put one? Let's do some cubic. When you have a graph like a cubic, and you want to give the interval of, let's say, strictly decreasing. Let's say we know strictly decreasing is pretty much going to be from here to here, because it's where the graph is going down. The challenge is what kind of bracket sets you use. For strictly decreasing, or increasing for that matter, you always want to look to the immediate right of the point. So if the immediate right of this turning point here, from here to here, is less than where you started, then that point is included. So in this case, x equals 0 is included in the domain. Whereas here, it's not included. So let's say this ends at 2. If you look immediately right here, the next y value is bigger than the previous y value. So you don't include that one. That's the nuance about that. VCAR always assumes you're looking right, not left at the point. Because if you assume left, then you'd have the opposite effect, where this one will be inclusive and this one would not be inclusive. So it's a thing that gets a lot of people. I'm not particularly sure why I put it in the calculus chapter, but I guess it's here, because technically speaking, I guess you can find these with derivative being 0. Right? Anytime you have a flat point, that's when you have gradient 0. Is it clear enough, the nuances as to why we have to worry about that sort of thing with the brackets? Okay, that's that. Next up, plot of the gradient function, so plot of the derivative. So we said earlier that the derivative is a function which describes the gradient of the original function. So what that gives us is a bit of a challenge into how do we interpret a gradient graph. So a gradient graph is just a derivative graph, which means dy on dx, or f dash x, is on your y-axis, and you still have x on your x-axis. Now, when you have a graph like this, which I'll just sort of replicate on the handwritten section, because dy on dx is on the y-axis, it means gradient is on the y-axis. So anything above the x-axis means positive gradient. Anything below the x-axis means negative gradient. Don't get that confused with the gradient of the graph itself. This graph has an always positive gradient. It's always pointing up and left. What this is telling you is the gradient of regular y of x, the original function, is positive on this side and negative on this side. More importantly, it's telling you the gradient is not only positive here, but getting more and more positive. It's getting steeper and steeper. Whereas on this side, not only is it negative, but getting, again, steeper and steeper, but in a negative direction, because it's getting more negative. Is it clear enough how a graph like this can be used to interpret the gradient of the original graph? Because this gets everyone. Like they'll always be confused on whether or not you sub things into gradient, into derivative, or into the original. All I'm trying to highlight here is use derivative.
I'm kind of confused.
Yeah, okay. So whereabouts did it start breaking down? When I had this graph up?
What?
So when I had this graph going, was that where things started getting difficult to follow?
Yeah.
Okay, cool. So maybe what I'll do is I'll do an example of comparing the two graphs. So let's use that quadratic from earlier. That can be our original function. So that's y equals x squared. Now the derivative of this would be 2x. So this is f dash derivative is equal to 2x, and the graph of 2x just looks like this, right? So the way this works is, for derivative, because gradient is on the y-axis, it means that all of these y values are gradient values of the original. So looking at this, I should be able to tell that anything on this side of the graph is all positive gradient because, positive gradient of the original, because it's all positive y values, right? This is the positive section of the y-axis, so we have positive gradient. And sure enough, that's what we have, right? These are all positive gradients. Whereas on the left-hand side over here, because you have a bunch of negative y values, these are now negative gradients, which makes sense if you look at the original again, because now you can see that all the curve is pointing down. It's all negative gradient on that side. Is that any clearer?
Yep.
Cool. Okay. Oh, I even had an example here as well. Nice. On the screen share. Sketch the derivative of the following graph. So that sort of thing that we just did there, where you have an original graph and have to then sketch the gradient, you may or may not be given what the actual f of x is. So again, if we highlight our attention to the screen share, we know it's a cubic, right? It's got two turning points and it goes, You could even say it's a negative cubic, actually, because it's going top left down to bottom right. But we don't really have enough information to be able to do anything with that because, this is not x equals -2. We got x equals 0, so that's cool. But we don't really have those x-intercepts to make the actual cubic formula. So if you're told to sketch the derivative of this function, you're not really going to be able to just use the table from before and then literally find the derivative of the rule. You're going to have to use the fact that derivative is talking about gradient. Here's what makes it easiest to do. You start by identifying where the turning points are of the function. So that's going to be here and here, right? You don't need exact x values, you just need to know roughly what these are. The reason why you start with the turning points is because that's where gradient is 0. It's perfectly flat. Because gradient is 0, that means that on the derivative graph, those should be x-intercepts. Because remember, your y-axis is gradient, and so for that reason, y equals 0 means gradient equals 0. That's how we're going to have x-intercepts for our derivative graph that are located at the turning points of the original. From there, split your f of x up into sections just based on the turning points. So you split it straight down the middle of each of those turning points. And then you look at each individual section and figure out if the gradient is positive or negative overall in those sections. Like in this case, it's pointing all the way down. So we're going to have a negative gradient that's eventually getting closer and closer to 0. Negative y values that are getting closer and closer to 0. Section 2, net positive, right? Starts at being flat. It's pointing upwards until it hits flat again. So positive values that curve down back to being 0. And then for section 3, it's obviously the same sort of thing. Pointing down and then going down forever. So you're going to have negative gradient values that are getting more and more negative. That's how you can, broadly speaking, do it for any type of graph. Is it fair enough, that approach? Splitting it up into turning points and then looking at the overall gradients. Cool. Here's some further tips, because usually you don't have just some really crazy graph. Usually you can know what the graph is going to be, roughly speaking, like this being a negative cubic. Now, for those who are already really familiar with derivatives, when you find the derivative of a cubic, you get down to a quadratic, right? That's what this was up here. When you have x to the power of n, so x to the power of 3, that's going to drop down to something like x to the power of 2. Because you know a cubic is going to drop to a quadratic, and more specifically, because it's a negative cubic, it's going to drop down to a negative quadratic, you know, roughly speaking, that when you draw your final graph, you should have a negative quadratic sitting there. So it's a nice little thing that you can just have that can really help you speed things along, rather than having to go through the entire process that I just outlined. If you can see what type of function you have, then you can use these shortcuts like that. Fair enough to shortcut? All right, that's it. You can do derivative on the CAS. So if this is a new concept for you and you're looking to just sort of do as many repetitions and questions as you can during the class, then using the CAS, sure, go ahead. It's this notation on the Casio or on the TI Inspire. You can do it this way. So yeah, feel free to cheat out a few derivatives that way if you just sort of want to check your answer or just sort of keep up overall. But ideally, at least in your own private study, you'd be using this table, trying to really understand, hey, when I have this, I get this. For Unit 1 and 2, you're only caring about this. So only ever looking at the power function stuff. All of this is in here because it has applications in Unit 3 and 4 as well. That's it for that PDF. Any questions that you'd like me to clarify on that stuff? Okay. Last up, we'll do just the chain rule. This is focused for Unit 1 and 2, so we'll just do the chain rule one for this one. Because Unit 1 and 2 doesn't do anything else like that. So, you would use the chain rule when you're trying to find the derivative of a function that appears to be made up of two entirely different functions. Like, for instance, you have natural log of x squared. There's no way to really, well, I'll take that back. There is a way to split this up in particular. You could use the log laws to take the 2 out the front. For the sake of argument, let's say we're not going to do that. You can see that this is made up of the natural log and the x squared. You have two distinct functions that you typically don't split up. Now, for the logarithm, you can, but if you don't want to split it up, you could use the chain rule. Basically put, if you don't have just x in these basic functions, if you have anything other than x, like even just 2x or x squared, like we do here, then you use this, which is the chain rule. Finding the derivative of that function means first finding the derivative of whatever's on the inside, and then multiplying by whatever's on the derivative of the outside. So here's how that looks. Define a new function to be whatever's the inside. All right, so you have natural log of something. That something is its own separate function. From there, because you've defined it as its own separate thing, you can now rewrite the original equation with that letter. So g of x is now x squared. We're just going to replace x squared with g. From there, find the derivative of the inner, so derivative of g. That's going to be 2x. We saw how that one worked earlier. Power goes down the front, and the power gets reduced by 1. Then find derivative of this one here. So we have natural log this time. If we look at our table, natural log of g, 1 over g. Right, we're just replacing the x with the g. That gets us this. Chain rule just says, grab this, multiply it with this. So we have 1 over g times 2x. And all we're going to do is put back what g actually was, because we want to have everything purely in terms of x at the end. So instead of having 1 over g, we now have 1 over x squared multiplied by 2x. That's pretty much it. And then you just simplify. So, in summary, you use this whenever you have what's referred to as a composite function, when you have a function that has another function inside of it. That's about it for the lecture part. Any questions on that? In the meantime, I will find the notes for this one, and then we'll do some breakout rooms. 3, week 6. There we go. So this covers a lot of different chapters. It's going to cover, I believe, if I remember correctly, 17b to d. So doing basic derivatives and then graphing that. And then the chain rule stuff, which is 20a and 20b. That's obviously a lot of work. We're not expecting to do all of that. In fact, even if you have other things you want to do in the breakout room instead, feel free. That's totally fine. I'll make the rounds. I guess that'll be it. Make sure you grab a copy of that Unit 1 and 2 book. Alright, let's make this happen. They've changed the UI of Zoom yet again, so if I stuff this up, blame Zoom. Okay, that's that. 1, 2, 3, 4. Yeah, cool. That'll do. Alright, I'll do the rounds. See you guys soon. Hey, how's it going? Oh, right, because you don't have a mic. Oh, that's right. You are pinging the entire chat, by the way. I'll say that much. Yeah, you're good. Damn, how's this going to work then? Do you have anything specifically you'd like me to have a look at? I know it's kind of hard to maybe do it over text. Maybe if you have like a photo of a thing you'd like me to have a look at, I can do that.
No, my mic
Oh,
works.
oh, it
Sorry.
does. No, I remember
I just
someone.
prefer to
Yeah.
text, yeah.
Okay, I remember someone told me they weren't going to talk in the actual thing because they had like a mic issue or something. All good. Yeah, totally. So, was there anything you'd like me to have a look at?
No, not really, to be honest.
No.
I wanted to ask you, what is this course for Unit 1 and 2?
This specific class is focused as if you were a Unit 1 and 2 student. Now, this stuff is being used for Unit 3 and 4.
Of course, yeah.
Like being able to do derivatives, it is a fundamental thing. Um, but yeah, the class 3, yeah, class 3 is supposed to be a hybrid. So it starts out being Unit 1 and 2 stuff, ends out Unit 3 and 4 stuff. Class 1 is predominantly Unit 1 and 2. Class 2 is predominantly Unit 3 and 4.
Okay.
That's the
Yeah,
gist of
I
it.
think I must have been joining the wrong class this whole time. I meant to be class 2, I guess, because, I'm
Yeah.
finishing up Unit 4 right now.
No, you can join all of them. That's perfectly fine. It's as long as you're getting value out of it, right? And maybe you are, maybe you're not. It's in the curriculum. So if you have a look at the Mastermind Premium Unlocked module, it'll tell you what's being covered and when. That'll make you, well, that'll give you a more informed decision as to whether or not you're going to get a lot out of the class. Sometimes we do breakout rooms as well. So if you do have questions like that, then whatever the curriculum is, you can still join in and get the
Oh,
value out of
yeah,
that.
of course. No, yeah, all good.
But yeah, just letting you know ahead of time if you don't want to join a class because you've done it already before, then that's totally fine. It's up to you, man.
No, all good, yeah. I'll probably just put it on in the background. So how do breakout rooms work? Do you go from room to room?
I go from room to room. Yeah, so basically what I just did here, which is I'll ask you if you got anything you want to have a look at. Someone will ask me a question. I'll sort that one out and then I'll move to the next person. Rinse, repeat until end of class.
All right, yeah, sounds good, man.
Easy. All right. I take it there's not much else for me to have a chat about, so I'll do some more rounds.
See ya.
Take
Take
care.
care.
Hello, hello. How are you going?
I'm going kinda alright.
Kind of all right. Okay. Is it with this kind of stuff or your own kind of stuff?
Um, with both. I don't really understand like differentiation, like derivatives. I just don't know. Like, do you have to like remember like all the equations?
No, you actually don't. That's the good thing about the derivatives chapter. All of this stuff shows up on your formula sheet. So as long as you can look at this table and know what it's telling you that you can do, that table is going to be available for you anytime you do derivatives. So is it fair enough how this is laid out? Like derivative of this kind of function is solved doing this. Derivative of this kind of function is solved doing this.
Okay.
That's fair enough how that works?
Yeah, yeah.
Okay, because yeah, I guess if you can follow this kind of working out, like how you would split things up and make it easier to do derivatives, then all you ever have to do is look up on this table. In fact, I'll show you exactly what you'll get in the real exam. So let's see here. Exams 2024. Yeah, we'll get the most recent one. Whether it's the exam one or the exam two, it'll be the exact same thing. You get this formula sheet here, which you'll notice has those things that I just discussed on this left hand side. Now they put some A terms in there. These are little chain rules they've solved ahead of time for you. That was the last thing we had a look at before we did the breakout rooms. When you have anything other than just x in the brackets, you do things a little bit differently. Is that your main concern with doing derivative stuff?
Yep. Yep.
Okay. So, like, if you have that to look at when you're doing your own work, are you happy enough to do that yourself?
Oh, okay, yeah.
I'm just asking, like, are you like that's you're allowed to say no if you want me to do some with you.
It's okay. It's okay. Like so in like a SAC or an exam, they give you a formula sheet.
Yeah, that's this.
Oh,
Yeah, so you get this in your tech free and your tech active. in your tech active, you also get to bring your own bound reference. So you can bring
Oh,
whatever you want, which means one of the things I recommend for people is actually just downloading copies of these and then stitching them all together in the book, because you can
mm,
just put them all into one big PDF. There's online tools that let you stitch PDFs together, and you go to Officeworks and you print it off with a big bound reference. Like, I've got an AI background, so I don't know if this is going to show up, but let's see. Um, Obviously, I didn't have my resources when I was studying. I made them. And so what
oh,
I had was this big, thick book, which was all four binders for all four terms. And it's this
mm.
massive spiral bound thing that I did at Officeworks.
Whoa.
And so, you know, you can do something like that with these notes here, which is essentially bind them all together, Officeworks, and then you just have all this.
Okay.
You know,
Okay.
that's just a recommendation. You can do whatever you want. You can bring any maybe only the ones you actually would look up. But yeah,
Yep.
is that all good?
Oh, I have a question.
Hmm.
Like it's like for my school,
Yeah, yeah. Let's see it.
chapter 17A.
17A of this book.
Yes. Question 3.
Question 3. Okay, let's suss it out. In the meantime, I should get my other camera in here so it's not lagging behind. Let me do that. 17A question 3, not this one. Two points on a curve. Find the gradient of PQ, hence find derivative. Okay. Was it fully unstuck on this, or did you get part of the way through it?
Fully. I don't
Fully.
really do good in like worded question.
Okay. Question 3 is actually identical to question 1. Did you do question 1?
Nope.
No. Okay. So did you do any of them from this chapter?
No.
Okay, that makes sense then. So this is the first time you're seeing the chapter. So what you have are 2 points on a curve. Now this one's a bit nicer because you have an actual point, 3 comma 3, and then you have another point associated with it. But it's essentially the same thing, which is, do you know how you find gradient between any 2 points?
Is it like y1? Oh, y2 minus y1.
Yeah, yeah, exactly that.
No.
And so that's all we're doing. Now, the points look massive and complicated, but it is still just going to be y2 take y1 on x2 take x1. It's the exact same thing. And so maybe what we'll do is, we'll do question 3 just because that's the one you asked. Okay, camera's finally made its way in. Let me turn that on. There we go. Okay. So we are going to do, as suggested, y2 take y1 on x2 take x1. So gradient, that's the first part. Find gradient of PQ. So gradient of PQ means you have the point P, x1, y1, and then you have the point Q. We'll call that one x2, y2. Sound fair so far?
Yep.
Okay. So to do gradient of PQ, M is going to be y2 minus y1 on x2 minus x1. And so whatever's in the y2 spot, I'm just going to put in the y2 spot. So we have Q, which is a nasty thing. It is x plus h all squared minus 2xh. Oh, 2x plus h, sorry. That's the whole y2 that we see in Q. And then y1 is x squared minus 2x. So minus x squared minus 2x. So this one here is y2. This one here is y1. Good so far? Maybe?
Huh? Yeah, it's
Oh, it
going.
was? Okay. And then, yeah, x2. That one's not so bad. That's just x plus h. and then x1, so minus x1, that was just h. Oh, sorry, no, it wasn't, it was x. And so all you would do from here is just simplify this nasty thing, which, is nasty, but it is just a polynomial at the end of the day. If you were to try and simplify this, what are some things you could see that you could do?
Take remove the x from down there.
Yeah, that's it. Those will cancel out nicely. Just got a h on the bottom now. How about on the top, if you were to simplify what's going on there?
Perfect square.
Yeah, perfect square expansion, for sure. So you're going to have x squared plus 2xh plus h squared. Might as well expand that one as well. So minus 2x minus 2h, and then putting the negative through those brackets. Negative x squared and then plus 2x. All of that on h. Now from here, we're just collecting like terms, yeah?
Yeah.
So let's see, we've got an x squared and a minus x squared. Those are going to disappear. We've got a 2xh, and that's pretty much it for that one. So let's leave that, 2xh. We've got a h squared, and that's it. We got a minus 2x and a plus 2x, so those are going to disappear. And we got a minus 2h. All of that divided by h. What's the final thing we would do to simplify this?
Factorize.
Yeah, you can do it in steps, which is factorize the h out and then delete it. But because you can already see there's a h in the bottom and a h in all of the top, I like to do that all in one line, which is just knock down a h off of everything.
Okay.
Do you see how that knocks down?
Yeah, yeah.
Yeah, it's the same as if I just put a h out the front and then killed it at the front.
Okay.
Yeah, that's the answer. So that's at least the first part of that answer, which is find gradient of PQ. Now, it then says, hence find the derivative of the function. Now, it says x squared minus 2x. You might notice that these points existed on the curve, x squared minus 2x. What's happening here is differentiation by first principles. Were you here for that lesson?
Like the online one?
Yeah.
No.
Okay. Were you here for the, well, not here, but there, I guess, for your school version of it?
Yeah.
Okay, cool. So maybe it won't take too much time to remind you what differentiation by first principles is. But it was basically when you have the average rate of change equation rearranged to look like this. Does that look familiar on the screen share?
Kinda.
With h's instead of delta x's, yeah?
Yeah.
Yeah, that's right. And so the whole goal was to do what we just did, which was expand everything on the top, kill the h's, and then what you do is you sub in h equals 0 at the end. That gives you the derivative. That is what find the derivative is. So when it says hence find the derivative, now we take this m value that we have and we just throw in h equals 0. So our derivative, dy on dx, is therefore 2x minus 2. Okay?
Okay.
So to cap it all off, basically, the way you know what to do is you have 2 points on a curve and you want to find the gradient. Well, 2 points gradient, that means rise over run. y2 take y1, on x2 take x1. From there, moving on to when it says derivative, that just means putting in h equals 0.
Wait, how do you get like the x values?
Those were already in the points. So you see how it's got x here, I got x here, x squared, all those?
Okay.
They were already in the point.
Okay.
Like if you do that exact same thing over here, you're not actually going to get derivative, but you're going to get derivative specifically at x equals 3. Same thing here for x equals 4. This one, because you're not given an actual point, you just got given x, you have it for all values of x, thus getting the derivative.
Okay.
Reckon that's enough to go off of?
Yep.
Cool. If not, you've also got the resources and you've got the video guides, and I've done a class as well last week on diff by first principles, so you can have a watch of that past recording if you like.
Okay.
All right, I'll leave you to it.
Yep.
Hello. How are you?
I'm good. How are you?
I'm doing good as well. I'm curious to hear if you got anything you'd like me to have a look at.
Um, Not really, not right now, but I'm studying for my SAC
Mm,
for probability.
sure. Okay. Um, but there's nothing from there you want me to have a look at?
Not yet. But could I send you some stuff if I get stuck on anything?
Yeah. Yeah. There's not too much more time, so if it does get closer to end of time, still just send it to me and I'll do it after hours. Okay?
Alright.
Yeah. And I'll send like a. In fact, do I? I don't think I have your number because I can't actually send a voice memo over school. Um, do you have my number? Did I ever give you that?
I think I have it, yeah.
Yeah, maybe send it over that way. That way you can have a voice thing as opposed to a text thing, which I know can be. I don't know. Do you think voice would be better than text?
Yeah, I think it'd be easier.
Yeah. Okay. Cool. All right. Well, that's about it then. Probability. So that's everything. That's yeah. That is soon, isn't it? Because you're doing all the probability. Actually, yeah. One thing that I've noticed. It's been. I'll drop this in the chat, which is it's a guide that I was putting together a while ago. It's a bit incomplete in the sense that all the examples feel like a lot to look at. If you just look at the first like 37 pages or so, what it does is it teaches you how to figure out what kind of probability you have, essentially. Because what you might have noticed is when you're doing these extended responses questions, the probabilities change every single time. Like they keep
Yeah.
changing and changing and changing. This guide here is supposed to help you basically look for keywords to figure out what kind of probability you have. Like, do you ever find that challenging in the extended responses?
Sometimes it's like hard to like differentiate which
Yeah.
one to use. Yeah.
Yeah, okay. So this is just like an overall guide that I've just sent to you now that basically talks about essentially that. So cool. I can leave you with that. And if you have any questions, yeah, I'll be here to field them.
Thank you.
Easy. I'll leave you to it.